Yeah, thank you for the introduction. The next 30 minutes, we'll talk about databases on Kubernetes using a custom operator on day 1, 2, and a year later. And actually, we do have databases running in Kubernetes for a year now. So before we begin, this is me. My name is Johannes. I'm working for a database company. The database company is called Neo4j. It's a graph database. We store things a bit differently than you would expect from a relational database. But actually, I'm not a database guy. I'm more like a container guy, which is good because we're at KubeCon, right? And we do have a team at Neo4j building Neo4j Cloud. It's kind of a managed Neo4j as a service, database as a service. And we want to talk about this today, about our story building this offering. But maybe before we begin, give me a short hands up. Do you building operators on your own? Do you have experience with that? All right, so there are quite some hands, and this is amazing. So if I'm telling something that didn't work out for you at all, please start the conversation with me. I would love to hear your story, what worked for you and what worked not for you, because I can only tell you what worked for us and what didn't work for us, and I would be super interested in what worked for you as well. Okay, so Neo4what? You maybe seen this logo before. Let me shortly introduce Neo4j because it helps the story. So you may have heard about the Panama Papers. So this was about taxing the fraud system. So people try to hide the money from the tax system, and they usually do this by opening a bank account in the Bahamas, in this case on Panama. And a few years ago, there was a leak of a law company in Panama. They leaked 11.5 million documents, like emails, scans, receipts, and this was 2.5 terabyte worth of raw data. And this was given to journalists. And as every sane journalist would do, they put the data into Excel. So they recognized that they didn't work out that well, so because they tried to find patterns of people trying to fraud the tax system. And in that case, they tried to find the pattern of persons that has a bank account, and the bank account is in a bank in Panama. So they didn't find any of those people trying to fraud the tax system, because people who want to hide loads of taxes are smarter than that. So they searched deeper and found another pattern. So there was the pattern of an address where the people lived, and there was another one living at the same address, and the other one was officer at the company, and the company has a registered bank account in Panama. And whoever tried to do a join over 7 tables in a relation database probably know that this can be potentially quite painful, but this is the data model of Neo4j. So we do have nodes like persons, and nodes could have classes, it's optional, but they can have relations. It's really easy to traverse relationships. And the great thing is, once you have found the pattern of those 7 nodes, you can query all your data set, all the 11.5 million documents, and you get all the people who try to fraud the tax system. So all the Formula 1 drivers who fraud the tax system and didn't pay taxes in their home country, or the football players, or the Russian noblemen, so all they were found through the journalism. And they use Neo4j for that, which is really cool. And there are also doctors trying to find the cure for cancer, and they're putting patient data in Neo4j and their treatments and how this worked out, and try to find a pattern to help curing cancer. And the NASA is putting all the engineering data, like decades of engineering data, in a graph to build up a knowledge graph to help to bring people to the Mars. So this is really, really exciting. But we also have more enterprise use cases. For example, fraud detection is it's really good doable by pattern matching or recommendations. So these are more enterprisey use cases. But what all of those users have in common, that they put their mission-critical data in a database, but it's not their core business to operate a database, to make it available 24/7. They need it 24/7, but it's not their core business. And this is why people tend to like as-a-service products, like databases as a service, monitoring as a service, metrics as a service, like all the products there in the exhibition hall. So we decided to build a managed database as a service offering. And we started over 2 years ago, and we started with a tiny web application, and in the web application, the user had a button to start a Neo4j instance. So we provisioned an EC2 instance, started a single instance Neo4j database on it, and then we reported the endpoint back to the user. This was our first iteration of the product. And we had an invite-only beta. We had roughly 50 customers using this, and it was not too bad. So this was okay-ish, but it had some downsides to it. The first downside is we forced the customer to give us a downtime, a maintenance window, while the customer allowed us to take their database down to do updates and fixes and whatever. And I don't think this is the way to offer a database as a service offering in 2.18 or 2.19. Furthermore, we relied on the availability on EC2, which wasn't that bad either, except we had some problems in August last year where we had really tough time, but I don't want to talk about that today. And we relied on fault tolerance on EBS. So we used block storage to store our data. And again, sometimes we had hiccups in EBS where it took up to 30 minutes to unmount the EBS from a failing instance to remount it to a new one. So this was also not really, let's say that way, our customers were not really happy about that. So we wanted to go away from single instance to clusters, because clusters promise to have zero downtime, because we can do re-roll-in updates on the fly and don't expose downtimes to our customers. And again, downtime was really bad, and availability is probably not the best thing in single instance. And while we were operating all the single instances in EC2, we were building all our management services, the UI services, the backend, or the workers. We deployed that on Kubernetes. So we're operating this on Kubernetes. We opted in for managed Kubernetes on Google, so we used GKE for that, because at the time we started, it was a really good and easy way for us to get started. So we gained experience over 1 year running stateless services in Kubernetes. And at that time, unfortunately, there was no graph database as a service offering, so we also bought in relational database as a service, because at that point, it was not our business to operate a relational database, so we just bought it in at that time. And currently, we are evaluating to change it to our own product, which is super, super funny. Anyways, so we had experience in Kubernetes running stateless services, and then we thought, we want to do clusters, but we don't want to do clusters on EC2 and doing all the scheduling on our own. So we thought we're going to leverage Kubernetes, the scheduling tools in Kubernetes. And then Kelsey Hightower gave a presentation.
Most people get really excited about running a database inside of a cluster manager like Nomad.
Kubernetes.
This is going to make you lose your job, guaranteed.
Yeah, so I'm still happily employed. But this was 2016. So Kelsey is right. So there's more in the talk. If you want, check it out. It was from HashiConf 2016. But then, this is just a backup in case the video didn't work. But last year, Kelsey said, Kubernetes made huge improvements to run stateful workloads, including databases and message queues, but I still prefer not to do it. Fair enough. And on the same day, in a further thread, Kelsey said, I think it's important to remember that Kubernetes only solves half of the problem. The other parts must be solved by stateful services and operational experience. And I think he's very true. And the great thing is, we had loads of experience, operational experience in running databases, and we were confident that we want to put it in Kubernetes. And we wanted to run clusters. So let's have a short look about clusters in Neo4j. Neo4j is a fully replicated database, so all the nodes have all the data. Neo4j implements the RAF protocol. It's basically a distributed algorithm to do distributed consensus, so commits in a distributed system. And it's basically like Paxos, just a bit weaker. So we have a leader-follower concept. You can write requests to the leader, and the leader would then go out to the followers and try to get the majority of commits back from them. And when he got the majority of acknowledges of the transaction, he would give back the transaction to the client and mark it as completed. We are running all the Neo4j instances in a dedicated stateful set. So we do have 3 stateful sets for cluster out of 3 nodes. We're using persistent volumes offered by GKE to store the data directories. And we do backup. We're using backup workers. And the end goal is, we're not quite there yet in the implementation, but the end goal is that we have the backup workers, and the backup worker is doing backups constantly, but he's not doing a full backup. He's doing an incremental backup. So most databases supports this. And this means that the backup worker holds state. That's why he has a PV attached to it. And he knows about the last backup and the last backed up transaction ID. So when he is requesting a backup, he would only synchronize the last transactions to it. So when we have that we're running backups constantly all the time, we maybe want to get rid of the PVs of the main cluster to gain more performance, because then we actually don't need it when we have the backup worker constantly doing the backups, and the cluster is fault tolerant by itself. But we're not quite there yet, and we're not decided if we want to go that step or not. So let's see and wait for the future. Okay, but this is cluster technology, so let's dive in Kubernetes and the operator. We started the operator, building the operator about 1 year ago, a bit before KubeCon Europe last year. And we decided to use the Go language to do it. As a Neo4j is written in Java, most of the other stuff is written in Python or Bash and other languages, so we didn't have Go experience at all, but we wanted to go with a language that Kubernetes is written in. So we decided to use the Kubernetes driver and the Kubernetes clients, and we're pretty happy to the day that we chose Go for that. We didn't use any operator kit or SDK or whatever, because they weren't just available at the time, and the actual code gluing our business logic on top of the Kubernetes API, the Kubernetes controller API, is just so thin that we didn't feel that we want to do it in the last year. So we stick with the vanilla code generated clients from the Kubernetes code. And in the data model of Kubernetes, and you probably all know that, you have like a loose set of resources. So you have deployments, replica sets, pods, stateful services, and so on. And the great thing about all those resources is that you have a controller attached on every abstraction layer. So you will have a stateful set controller who's doing a constant task reconciliation, and reconciliation is just a fancy word of comparing the current state to the target state. So he would ask for all the CIDs, and then he would calculate the target state. If this is not matching what is currently running in Kubernetes, the stateful set controller would decide to start a pod. And he does that by just creating a new pod resource. So then the pod controller would kick in and see that there's a new pod in the target state that is not in the current state. So then the pod controller would try to find a kubelet to start the pod, and so on and so on. And the great thing here is that we can extend that data model. So we can just add a new type and call it Neo4j database. And we wrote this controller logic so that a client could do kubectl apply whatever thing he wants to apply in the Neo4j database, and then the Neo4j controller would kick in and say, oh, there is something in my target state that is not in my current state, so I need to start a new stateful set, for example. And then the stateful set controller would kick in and do its thing, and then the pod controller, and so on and so on. And this is really great. So we're reusing loads of logic from Kubernetes itself, which is super helpful for building this product. But as we were developing the operator, this reconciliation logic got bigger and bigger and bigger. And we thought that we want to change that. So we split down the whole reconciliation logic in things, and let's call it mini reconciler for now. So we're splitting out logic for dedicated things in mini reconcilers. So we have a dedicated mini reconciler for backups, or mini reconciler for load, so when the user requests to load a database or restore a database. We have a dedicated mini reconciler for config maps or for certificates, so all the communication is encrypted, so we have a reconciler to create the certificates and put it in secrets, or for DNS entries so that the end user can access the database from the outside, and for the instances, and for eviction and PDB. So we just added last week a new reconciler for eviction, and we'll talk about it a bit later. So we want to talk to the Kubernetes, the GKE autoscaler, and want to give him hints when it's safe to clean pods and when not. And we'll talk later a bit about it. So we separated this. So our main reconciliation So the main reconciler basically just builds up the current state and the target state. And he does that by asking the mini reconcilers for their view on the world. So the main reconciler would ask the config map reconciler, for example, what is your current state and what is your target state? So he would gather all those mini information from the mini reconcilers, would aggregate it and declare it as the whole current state and the whole target state. And then he would loop over all the mini reconcilers. So they are ordered. And when everything finished completely, the reconciliation for that database would be marked as good to go, no, nothing needs to be changed. Or maybe there's an error on the way. So one of the reconciler marks an error, he can't talk to Kubernetes or whatever. So reconciliation would stop at that point, and the reconciler would fall to sleep and then maybe picks that database up in the next reconciliation loop. Or maybe one of the mini reconcilers requests changes. So we separate that the mini reconcilers are talking to Kubernetes, but they're reporting back to the main reconciler that they've changed something. So that the main reconciler would also stop at that point when one of the mini reconciler requested a change, and will pick it up in the next reconciliation loop again to give some time for the current action to take into place. And we're pretty happy about the current situation. Maybe it's not the most performant one, so maybe some of you have some suggestions how we maybe improve that, but so far it worked pretty reliable for us. And let's dive into some examples. So this box is a CID, so someone creates a new CID saying, I want to have a Neo4j database, so the reconciler would pick it up and decide that he wants to start 3 databases in the target state. So he would start the first instance, wait until it's healthy, and then the second one, and then the third one, and then he would mark the entire CID as healthy. So we're using conditions for that. We'll come back to it a bit later. But let's do the next example. So here, so we have 3 running healthy instances, so everything is fine, but all of a sudden one of the pods has a problem. So it goes back to 2 running instances that are healthy, and we want to start a third one to go back to the desired state. We have 3 running instances. So then the operator would just start a new pod, wait until it's healthy, and then the whole CID would be marked as healthy. And the great thing here about this reconciliation pattern is that this is the exact same logic for creating and healing. So we don't have dedicated failure handling here because we're doing target and target state calculation. So these are the exact same steps here. So this is really amazing for us. And if you think about how you would do this in a shell script, for example, this potentially could be pretty messy. But in this Kubernetes way of engineering, this is really clean and straightforward. Okay. Let's look how we update a database, how we do a zero downtime rolling update to a database. So when we request a change to a CID, and this could have multiple reasons, for example, there's a new Neo4j version, or we have changed resources, so the customer wants a bigger database, he wants more CPU or more memory or whatever, or he wants to reset the password. So Neo4j itself has user management, but maybe the customer lost the master password, so we can reset that for the customer. So we want to change it. And let's assume, for example, the lowest node is the leader. And the idea here is to prevent leader elections. So the leader, the one you can talk to for write requests, can change, but when you do an update, you want to not do this. You don't want to do more confusing in the cluster, so we want to preserve the leader as long as possible. Our strategy here is to firstly start a new pod so that we go up to 4. And as you noticed, the majority changed now. So in a cluster out of 3, you need the majority of 2 nodes to acknowledge and commit. But when you have 4 nodes in a cluster, the majority all of a sudden is 3. So Neo itself would cope with that so that you don't run into split brain scenarios or something. So now you have a higher quorum size. And if that node becomes healthy, the operator would start a new one. So then we have 5. This quorum is still 3 yet. And then he would start to stop old nodes. So he would start a follower. So we want to keep the leader being the leader, so he would start a follower. And then we would go up to 5 again, wait until the node is healthy. And then we have the target state. So this is the cluster we want to have. 3 healthy new nodes in the cluster. And then the operator would stop one of the followers, and then he would trigger a leader application. That means he asked that node to step down as a leader so that someone else can pick up the leadership. And after that happened, we stopped that node. And then our update is completed, and we can mark the CID as healthy again. Great. The next logical step is to update the operator. And our first iteration was we just deployed the new operator code. The problem here was, assume you have, I don't know, 50 or 100 running databases. So the operator, maybe you added a new feature, detected a change in the current state and the target state. So he would loop over all 100 databases and detect that there's something to be done. So he would do one baby step, start a new pod for every of those 100 databases. So all of a sudden you have 100 new stateful sets to be started. Probably don't have enough capacity in your Kubernetes cluster. So this would kick in the GKE autoscaler. So you will get loads of new kubelets to complete your deployment. And at the end, you have loads of new kubelets, and you have a low utilization. And this will cost loads of money. You probably don't want to do this. Maybe you want, and we didn't want to spend that much money. So we introduced a number. So the resources are aware of the operator number that is currently responsible for them, and the operator itself is aware of its current number. So the operator with a number 42, for example, would only pick up databases that are assigned to that operator. And when we deploy a new operator, operator 42, the first thing he does is nothing, because you don't have any resources attached to him. And now we ordered the data, we prioritized the databases in 3 levels, low, medium, and high. So low priority databases would be canary databases or internal engineering databases, so no customer attached to them. And then we would start with the low priority databases to roll them in and see if our change was good and if the databases can complete the updates and so on. And when we're confident that this is good for low priority databases, we can go to medium and high quality database, high priority databases. So if we then change maybe 20% of our databases of the low priority to operator 42, he would pick it up, he would see those resources in the reconciliation loop, and he would roll in like the first row of clusters. He would do the rolling update we just described. And then we would do it for medium priority and maybe lastly for the high priority. And if everything went good and no databases are left for the old operator, we can then safely shut down the old operator version because it's not needed anymore. And this is how we do like rolling deployments of the operator. But there's so much more to talk about. So we're in 23 minutes, so we have some time left. There's so much more to talk about. So we're using heavily conditions to reflect if a cluster is fault-tolerant or available. So in every reconciliation loop, we ask the cluster for higher level metrics. So is the cluster available? So do we have enough nodes inside the raft group to perform write requests? Or if it's fault tolerant, so we have quorum size +1. And we store it in conditions in the CID. And afterwards, we're using the conditions in metrics. So we're building dashboards out of it if the databases are fault tolerant or if they are available. So that our SRE team can kick in when a database is only fault tolerant, is only available for, let's say, 5 minutes, but not fault tolerant. They can actively go into and fix the problem to bring the database back to fault tolerance before it loses the availability. And as I teased you, we also do this for eviction and pod disruption budgets. So pod disruption budget basically says for the autoscaler when you want to roll in a new node pool to your cluster, that the cluster out of 3 nodes is allowed that you can take 1 node down at a time and to keep the cluster alive. But this is only for the happy case. So what if one of the nodes is currently catching up, so the cluster can't sacrifice any of the nodes? You can't, you could do it with the pod disruption budget, but there's an annotation you can set to a pod to tell the Kubernetes autoscaler to not touch it when rolling a new a new node pool. And this is the save to evict annotation. So we have a reconciler doing this every reconciliation loop, checking if the database is fault tolerant, and if the cluster is not fault tolerant, setting the annotation to stop the autoscaler from killing pods and bringing the cluster in a not really good situation. And we need to talk about Sitecast. So we try to stick to the official Neo4j Docker images as close as possible, and we're using the official Neo4j Docker images, but there's loads of stuff in Sitecast going on that we needed to add to make that happen. So we have Sitecast for logging, for metrics, for initialization, and for debuggability, and all that kind of stuff, because we wanted to be compatible to the official release. So when there's a new release, we can get it right away without going through an insane build pipeline on our own. So we're using the official images for that. And we added a thing for debuggability. So this is really cool, because when our operator was in a state where it was not as good as it is today, so when we needed to execute in the cluster quite often to debug why something is not working properly, we had the problem that we were in a race condition with the operator trying to heal the cluster. So we had loads of time that we executed in a pod to see why it's not working, and then the operator killed the instance underneath our shells. So we added a simple annotation, and we called it, we didn't call it do not touch mode, but it is a do not touch mode. If the annotation is present, the operator won't touch any of the pods or any of the CIDs, so it will leave it alone, so that we can go into and repair what we think we need to do to bring it back to life. And then we remove the annotation, the operator kicks in again for that cluster, and then takes over the operation for the database. Cool. Is everything happy then? Kind of. So we lost loads of pods over the time, loads of containers, but we didn't lose data, because we had the PVs in place and we had the backups in place. So this was really good. So as I said, we had some tough time when we had problems like we're doing a rolling deployment, our operator code is not as good as today, and then the autoscaler kicks in all of a sudden and kills some pods, and sometimes he killed the wrong ones, so the cluster was stuck. So then we needed to go in and recover the cluster manually and tell the cluster, okay, shut down those two pods, add the do not touch annotation first, shut down those two pods, then mark that node as you're the survivor, remove the annotation, so the operator kicks in and then does the thing. We have one healthy instance, and we want to have two more, and then he's doing basically the create algorithm again. So we had loads of this. And every time we did that, we tried to bring the manual steps we made into the operator code. So we tried to learn from that. OK, so we have some time left before the question, so I would shortly go over testing, because we really feel strongly about testing our operator code. And like last year in KubeCon, there was loads of discussions about testing. So I want to give you a short overview how we do it. So we do testing on different levels. So the first thing is unit testing. So we have loads of table tests. So please be patient with me. I'm coming from a Java background, so we don't have table tests. I'm super excited about table tests. So what we do here is we describe a fixture, so the current state, and then we describe our expectation. And then we have a tiny function like if the cluster is available, so the calculation if I have at least quorum size of available nodes. And this is looping all of those tests in the table test. So we have hundreds of those. And the next step up would be what we call integration tests. So we mock the entire Kubernetes API, and in Go language, there is a library to also make those calls spyable. So you can assert that something was called. In that case, we're testing a config map. The actual state is no config map is present. The desired state is that we want to have a config map, so we're mocking all this stuff. Then we ask the mini reconciler for config maps, please do the reconciliation, and we expect that this was true, so the reconciliation returned true, and we assert that create config map from the Kubernetes API was called. Okay, so the next logical step up would be what we call system integration tests, where you have your YAML files and you do kubectl apply your YAML file, and then you expect a running cluster maybe 5 minutes later or 2 minutes later, or whatever time span later. We don't have that in that case. What we have loads of automated end-to-end tests. So we had end-to-end tests from our previous systems, and those covered all the user stories we defined. And those automated end-to-end tests, they would use the same APIs as the UI would use. So we're not testing from the UI level, but from the API level. So we're using the end user-facing APIs to trigger a database create, and then we assert that somewhere in Kubernetes, somewhere later, there would be a running database. This is also really cool. And then, as I teased maybe before, we're running canaries. So in every environment, staging, production, and personal environments, we're running canary databases, so databases with no custom attached to it, but other processes running constant load against it, and we're running chaos monkeys against those canary databases in staging, in production. And this gave us so much valuable insights about the cluster technology, how to handle failure, how clients would react to failure. So we learned loads of those using chaos monkeys and also in production. Okay, this is the time to thank you all very much. If this would be interesting to you, please feel free to ping me, to talk to me. And if it's so interesting to you that you want to work with us, you can follow that sneaky QR code there. And most importantly, enjoy the conference. Thank you very much. So I have 3 minutes more of questions. Does someone want to ask a question?
Hi, thanks for your talk. You talked a little bit about leadership, election-aware operation of things. Could you talk a little more about the data aspect of operating databases? So, for instance, when you kill nodes and spawn new nodes, you probably want to make sure they spawn in a location where the data is available to limit copying stuff around. How do you deal with things like corruptions at the data level? Do you consider repairing things, or do you just kill the thing and try to get it from a backup or balance it from other nodes? So could you talk a little more about the data aspect?
Okay.
Thanks.
So I hope I got your question correct. So it was quite noisy here. So if I got it correct, the question was how to deal with data corruption in case of failure. So in the Raft protocol, it makes sure that you only can talk to the leader, and if you don't have leadership, you can't perform write requests. So beside the transaction IDs of the actual database, we do have transaction IDs for the Raft messages itself. So when the leader loses leadership, so when he's not able to ping the other nodes, if he would detect that he's in a cluster and don't get the correlated health checks from the other nodes, he would step down the leadership so that he would recognize that he's not allowed to write anymore. What could happen in theory, when you're on the leader, you get a transaction through, and you get only one commit back from one of the followers, but not from the other one, because maybe it's already petitioned away or something. And then you kill both of the nodes that acknowledge the transaction. This could potentially lead into problems when you just hit it in that situation. As I described, we're using PVs to that. So currently, it would not be possible to kill the entire state, because as long as you don't kill the remote storage as well, we wouldn't lose the overall data set from those two nodes. So we would then try to bring back the nodes based on those PVs. But if the PV is also gone, like both PVs, which we didn't have so far, then potentially we would lose the transaction because we don't have the data set, because this was like a failure of two nodes too quick after only those two nodes committed the transaction, and the third one didn't commit it, and the backup worker didn't got it. So in that case, you could potentially lose data. To be honest, we didn't lost a PV since we're using Kubernetes. So we're trusting Google to do good things with our persistent disks. And so far, 1 year of operating, we weren't disappointed yet. It doesn't say that we will never lose data, but so far with the persistent volumes, we were pretty good so far. Maybe if you want to talk more about it, maybe you can talk it offline. So I would love to hear about your concerns and what problems you probably experienced to ask that question in that form. Okay? Thank you very much. Thank you. Oh, cool. We have time for one more question. That's amazing. Thank you.
Hi there.
Hi.
You spoke about upgrading from operator 41 to 42.
Yes.
It seemed like a bit of a manual process. Have you gotten to a stage where you've automated that now?
Yes. So currently, this is a halfway automated process. So every deploys goes through a release pipeline. So the operator would be deployed when someone says that he wants a particular version going from staging to production. But then currently, the process, I think it's partly manual, where we say we deploy lower priority databases first, and when everything is happy, we go to the next ones. I think this is just like this, we call it phasing rollout of database updates. It's so new that we want to experience currently first with it. And when we're confident then our manual workflow is good enough, then we can put it in an automated way. But maybe I'm wrong, maybe I need to refer to our SRE people also in the audience to tell you the truth. But yeah, the end goal is to automate everything.
Ask a quick cheeky second one.
Yes.
How did you get to the metrics annotations that would be helpful to your SREs?
We calculated. So we do, in the mini reconciliation for fault tolerance and availability, we calculate if a cluster is fault tolerant anyways, because we're only doing certain things when the database is fault tolerant. So we calculate it anyways, and then we're doing the update on the CID in every reconciliation loop if we detect that there's a change. So this is something we do in code, basically. All right, yes?
Hi, so I'm also developing operators right now. So what's your tipping point for when you decide if something should go to mini reconciler or a different operator with its own resource?
So if I got the question correct, it was how we decide if we want to pass in something to a mini reconciler or to another reconciler? Or to another operator?
Its own resource, like for example, for service you have one operator, and for backups you have another, and one main operator that is reconciling those resources only.
Yeah, so this is a list of operators. So we do have all operators in the list, and we think we found a good way how to find the sequence of operations we want to go through. And then we always want to go through the operation, through the reconciliation of one mini reconciler after the others. So we're only passing to the next one if the previous step was fine at that point. So if a mini reconciler in position 2 maybe requested changes, we would not go to the next level. We would wait to the next entire reconciliation loop to then check in step 2 that everything's okay, and then go to the next step. So we're always going through the entire sequence of reconcilers, and only we're going to the next step if everything was fine in the current step, and then go to the next one, and then go to the next one, and go to the next one. Okay?
All right, one more.
I'm interested in data too. It's not clear to me if when you talk about persistent volume, you are talking about file system volume, or if you're using some overlay, you talked about ABS from Amazon. I don't know if you're using an overlay, what kind of latencies and problems in performances it brings on.
Yeah, so if I got the question correct, this is about, we're using remote storage, so we're facing latency, yeah? So yeah, this is very true. I don't know how Google is managing this, but the latency is not that bad as you would expect it. So there's a blog post on the Google computing website where they say how much performance you get in order, like, related to the instance size, like the disk size you're buying. So you get more IOPS if you're buying big disks and so on. There's a huge blog post about that, and we're trying to get the best performance for our customers. But you're right. Always when you're talking to remote storage, you will lose performance. That's why we maybe want to change that in the future. For Neo4j itself, it's kind of easy in comparison to other databases because you don't have random reads so often. In Neo4j, you would have way more reads than you have writes. And most of the time, the reads can served by memory. So you don't have, as you would have in Cassandra, something where you have random access to whatever's place in your disk. You typically don't have that in Neo. So for the read, it's not that important because you mostly serve it from memory, so you don't have the performance impact there. And for the write, yeah, they take longer than if you would have like a single instance running on an SSD in the same box. Yeah, that's true. Okay, thank you very much, and thank you for all the questions.